Thank you. I would like to thank the organizer for inviting me and giving this opportunity to speak here. So before going to the title of the talk, I would like to spend some time to say about the history of or origin of this problem. So the problem arises in the study of irreducibility questions. Yes. Okay. So irreducibility questions of modular space. Of vector bundles over surfaces. So unfortunately, there is no general result, so good result for this irreducibility question, so whether modular space is irreducible or not. But so far, the best result known, general result is known to O'Grady, due to O'Grady. So what he proved that for sufficiently large C2, the modular space is irreducible. So let me fix some notation. So throughout the talk, I will always assume S to be a smooth projective surface. I will specify if I need some further restriction on that. Over complex numbers. So H is an ample divisor. I will not make any difference between divisors and line bundles. So I will write MH, MRC1, C2 is the modular space of semi-stable vector bundles. So H semi-stable vector bundles with fixed determinant with first chain class C1 and second chain class C2. Oh, sorry, I should say of rank R. And I denote M bar RC1, C2 with the moduli space of torsion free shapes. Yes.
H semi-stable in the mu sense, is it? Mu semi-stable.
No, it's H is ample bundle that fixing, and the Giesecke semi-stable.
Or Giesecke?
No, Giesecke semi-stable. So so far the question is whether this modular space. So this is irreducible. So the general answer is not known. So in general, the answer is not known. In fact, there are examples where this modular space is not irreducible. And the best result, general result is known due to O'Grady's. Yes?
The answer is no.
Yes. Okay. So the best result is due to O'Grady. He said that he proves that if C2 is sufficiently large, then this modular space is irreducible. So the question still remains open for small c2. So if C2, yes, the surface is underlying surface is K3 surface or rational surface, then this partial result is known for this. But if the canonical bundle is ample, Ks is ample, then the first initiative for the small Chern class, this question raised by Simpson and Mestrano. And what they have proved that they have considered X to be, here I am just specifying, so very general quintic surface. Means it's a degree 5 hypersurface in P3. So in this case, Simpson and Mestrano, they have proved that in a series of articles, they have proved that this modular space is irreducible. So they have considered the rank 2 case, and the H is in that case, H is OS1. C1 is H, and C2. P3, yes. So this is irreducible for C2 greater than or equal to 4, and otherwise it is empty. So then next natural question arises for the what can we say about that higher degree surface. So for example, my initial goal was to investigate this question for very general sextic surface, the next case. So but Simpson and Mestrano, they gave an example that if C2 is equal to 11, S is very general sextic surface. Then the same thing, 2H 11, this is not irreducible. Sorry? From P3. Yeah. So this is not irreducible. In fact, they have computed two different distinct irreducible component, and they have conjectured that, that is the conjecture I mentioned here, the Simpson-Mestrano conjecture. So they have conjectured that those are the two only components. So I just, let me write down the components. So I just write M1. M1 is the set of all vector bundles in 11 such that it sits in an exact sequence of the form IZ1, where Z is a zero dimensional subscheme of length 11. And Z lies on a rational cubic so if E fits in an exact sequence of this form, this where IZ is the ideal shift corresponding to Z, and the Z is a zero dimensional subscheme of length 11, and the Z, the property of Z has that it lies in a rational cubic. So consider all the such vector bundles that will constitute an irreducible component, and another is M2. So this is again same. So Z lies on a plane. So these are the two irreducible components they have computed, and they have conjectured that this modular space has only these two components. So one thing is that if any vector bundle which belongs to this one of these components computed by Simpson and Mestrano, then that bundle has a section, right, non-zero section, because they are obtained by this kind of extension. So yes. So now our first observation is the following. So so my initial goal was to prove the irreducibility questions in other case when C2 is not equal to 11. Then for that, what I studied, I was trying to classify the obstructed bundle. I will explain all those things in a minute. Then, so what from there, that classification, we can, and one more observation, what I am going to write next. These two together will say this conjecture is true. So first of all, the first observation. So first observation is that following. So if E belongs to MH11 such that H naught of E is not equal to 0, then E sits in an exact case of this form E I Z1. Then what is our observation is that in this case Z lies in a plane or in a rational cubic curve. So that means if any bundle which admits a section, then that belongs to one of these two components. So the next observation, so next theorem, so if we prove the following theorem, so the theorem I'm going to explain that this theorem says that there exists a bijection between the irreducible components of M2HC2, sorry, and sigma C2, I just, what is it? This is equal to all those E such that for C2, where C2 is less than equal to, okay, so for C2 less than equal to 18. So if C2 is less than equal to 18, then there is a bijection between the irreducible component of the modular space and the irreducible component of this subset of the modular space, which consists of the bundles which admits a section. So if we prove this theorem and assume this fact, if I get time, I will give a proof for this also. And these together will give a proof of the Simpson's conjecture that this modular space has only two components. Yes.
Do we know that those sets are irreducible?
Which one?
M1, M2?
Yeah, that you have computed, right?
I remember.
Yes. I think you have proved that these two components are irreducible. Okay. So then these two, yes. So these two observation and together will tell that this is, in fact, it's true fact. So now the main difficulty to prove this. So to prove this, we investigate the obstructed bundle. So what are the obstructed bundle, and if there is a so for that, what is let me define what is the obstructed bundle. So vector bundle E in general actually, but I just for particular case I just write down, is called obstructed non-zero. So, so in particular, if E is a unobstructed bundle,
Is that H? What did you write? H0, H2, or
H2 dimension, or you can say this vector space also. This is non-zero. This is stress-free endomorphism, bundle of stress-free endomorphism. So, if E is an unobstructed bundle, so note that then unobstructed means this is 0, H2 is 0. Then E is a smooth point. Smooth point in M. So what we prove? So we prove the following theorem, that if C2 for C2 less than equal to 18, then in bundle, then a vector bundle E C2 is unobstructed, sorry, is obstructed if and only if H naught of E is non-zero. So this is the first statement we will prove. So if we suppose we know this, then how that theorem will imply this one? So that is because, so for the moment you assume this, that this is true. So then that means if, so we consider a vector if E belongs to that modular space 2HC2. So let such that H naught of E is 0, sorry, is unobstructed. Yes?
I mean, the smoothness here is given by an element in H2 of the endomorphisms of E, but not twisted by the canonical. So I'm a bit confused here.
Sorry, this is H2. I am sorry.
Oh, well, that third duality is.
This is H2. I am sorry. Thank you.
In H0,
Yeah, the deformation maps you were saying this is 0, yeah, then that's a smooth point. Yeah, but I'm not saying this is sufficient condition. I'm saying if this is true, then it is.
What you're saying is true.
Yeah, that's what I'm saying, yes.
In that case, the dimension will be bigger.
Dimension will be bigger, yes, exactly. Expected dimension, more than expected dimension, yes.
I see.
So if E belongs to this, then such that E is unobstructed. So this will prove this theorem. This will imply this theorem because so the components are so this irreducible components of this are in bijection with the irreducible component of this. If we provided for any unobstructed bundle, it belongs to the closure of this. Now, this is quite easy to see because if E is unobstructed, then it is since this is 0, so it is smooth point. So the component containing this has expected dimension. So if this is the case, then so if E is unobstructed, containing E has expected dimension. And one can compute the expected dimension is equal to 4C2 minus 39. On the other hand, if H naught E, if H naught E is non-zero, is equal to 0, then the Euler characteristic of E, one can compute that this is equal to 19 minus C2. So this is strictly greater than 0 provided C2 is less than or equal to 8. That's why the assumption is there. So that means H naught of E plus H2 of E is strictly bigger than 0, but this is 0, that means this is non-zero. So E sits in an exact sequence, so this is same as by Euler's, by dual. This is same as H naught of E1, one can see this is. So that means E sits in an exact sequence of the form minus 1, where the coordinate of Z, where Z is a length is C2 plus 12. So this computation is not so difficult. Now there's one result due to Simpson and Mestrano. I just recall that. So any irreducible component of the bundles is sitting inside of the form 1 has dimension at least greater than or equal to 3C2 minus 20. Yeah. So any irreducible component of the bundles E sitting inside in an exact sequence of the form this has dimension, bundle means I am saying semi-stable. For stable, actually semi-stable and stable are same here in this case. So has dimension greater than or equal to 3C2 minus 21. But here we have a computation that this has expected dimension 4C2 minus 39. And this has dimension 3C2 minus 21 greater than or equal to this. But that dimension is smaller than this. Yeah. This one? So what I am saying that any irreducible component of the stable vector bundles E sitting in an exact sequence of the form this has dimension at least 3C2 minus 21. Every irreducible component has dimension at least this. But this says that it has expected dimension 4C2 minus 39. So, but 3C2 minus 21 is bigger than 4C2 minus 39, at least for C2 less than or equal to 80. So that means there does not exist any component which consists the bundles with H naught E equal to 0. That means that bundle is in the closure. So that will give a proof of this theorem that there is a bijection between these two. So now we have to prove this fact that if is a vector bundle, C2 equal to 18, less than equal to 18, then is obstructed if and only if HE not equal to 0. So we will give a proof of this. This is very elementary proof. But this is for this we need to recall some interesting theorem, very well-known theorem called Alexander-Hirschouitz theorem. So before that, I just write down few exact sequences. So let us assume that H naught of E is 0. Then as you have seen there that C2 is greater than less than equal to 18, so it has a that Euler characteristic says that
That
yes.
inequality you wrote is should with the other way. 3C2 minus 21 is greater than 4C2 minus 39.
Yes. Sorry?
At 18, I think it's equal.
18 is equal. Uh, 54. Yes. Or then maybe some calculation is wrong. Maybe 17 then it could be yes. Yeah, for 18 it is equal. Okay, so maybe. Okay. So if H is not equal to 0, then that Euler characteristic computation says that E sits in an exact sequence of the form O minus 1 to E to IZ to 0. So from here, since E has determinant of E is equal to O1, so we have this identification that end node E tensor is isomorphic to C into E. So which gives an exact sequence E tensor I think O minus 2 IZ square 3. This is IZ square. So if we tensor with K, then we get, so this will give you yes, we have here K is actually we have E minus 1 tensor Ks so here K is O2, K is note that this is equal to OS2. So we have the following sequence 0 to E So this is the identification we have. So you just take this symmetric S2, then use this identification. That will give this S2 of E to there's a IZ square 4, and then tensor with O minus 1. That will give this. So this will give you, if we consider the H naught, this is less than equal to H naught of E plus h naught of I z square 5. But we are given that this is equal to 0. So this is less than equal to h naught of I z square 5. Sorry?
Why is that not U1?
1
On the left?
here, e minus 1. Sorry. Minus 2, sorry. E tensor of minus 2. So this is the exact sequence. I am tensoring this by k. It's fine. Okay, so this says that h naught of this is less than or equal to this. So so only thing is now we have to check that if we can prove that this is equal to 0, then we are done. That means this h naught is 0. So is unobstructed. Sorry, is unobstructed. Right? So it means what? We have to prove that this is I z square 5 means any degree 5 hypersurface section cannot have singularity at z. It's a double point. I z square means a double point. Singularity along z. So it remains to prove that any degree 5 hypersurface section cannot have singularity along z. So one more thing I forgot to mention here, that when I write down this exact sequence, there, this z always satisfies Kelly-Becker property. So here I should say that z CV5. It means any degrees. It means any degree 5 hypersurface passing through z prime containing z with 1 passes through z. Because it's a vector bundle locally free, so z has to satisfy Kelly-Becker property for O5. So the state one theorem, which I will not prove right now because it will take time, because that is the longest proof of this paper. So the theorem this theorem says that S is a very general sextic surface. Very general in the sense that Picard is Z. Picard is Z. Picard is Z. Z, rank 1. Surface, let Z be a set of a zero-dimensional subscheme. Scheme of length L is greater than or equal to 17, satisfying CV5 So let X be a hypersurface of degree 5 such so if Z contained in the singular locus of S intersection X, then either Z sits inside lies on a quadric hypersurface or Z contained in the singular locus of X itself. Sorry? This one?
The line above.
Here? So Z contains the singular locus of S intersection X.
S intersection X.
Yes. So that means that this singularity, if Z has length greater than or equal to 17 and satisfies CV5, then all the singular points coming from only X. Elba correct property I have written here. Yes. So now I will prove a state the Alexander-Hirschouitz theorem. So this theorem says that so fix R is greater than or equal to 2 and D is greater than or equal to 2 and consider the linear system I explain what does it mean. 2pi consisting of hypersurfaces degree D at most D and in R plus 1 variable D at most D in R plus 1 variables that are singular means here I just allow note double point singular at n general points pi then L has expected dimension and that is equal to expected dimension is minimum of -1 R plus D choose D -1 minus n into R plus 1 provided the triple RDN is not of the form following form is 2, 4, 5, 3, 4, 9, 4, 4, 14, and 4, 3, 7. So in particular, in our case, R is 3 and D is 5.
What is min minus 1? What's
It could be, yeah, it could be negative, right? So -1 means empty, I'm saying. Maximum, yes. Oh, I said minimum. I'm so sorry. Thank you. Yes. So in our case, R is equal to 3. And so only R equal to 3, the only exception is this. So only if D is degree 4, so degree 4 hypersurface can have singularity at 9 points, 9 general points. Okay, so this expected dimension for this is 0, right? If we take 3, 4, 9, then if we computed this, then this is equal to 0. But still there can have, that means there doesn't exist any degree 4 hypersurfaces if this is of expected dimension. If D is equal to 4, then the expected dimension of L is equal to 0. That means there doesn't exist any degree 4 hypersurface which has singularity at 9 general points. But that is not the case. This is the saying that there exists a degree 4 hypersurface which has singularity at 9 general points. So if in our case D is equal to 5, we have to find out, we have to prove that this is equal to 0. So we will consider only the degree 5 hypersurfaces. So for degree 5 hypersurface, there is no exception. So if we find, so that means, so that if we apply here, then there doesn't exist any hypersurface of degree 5 which is singular at 14 general points. General point in the sense which imposes independent conditions. So therefore, now this theorem says that if there exists a hypersurface section which is singular along Z, then that is singular of a quintic hypersurface, right? But Z has always length greater than or equal to 17. So this implies that any 14 point in Z, so suppose there exists X of degree 5 hypersurface which is singular along Z, then any 14 points of Z fails to impose independent conditions. Right, because general point it imposes independent conditions, then by this theorem that Alexander-Hirschouitz theorem, that there doesn't exist any hypersurface of degree 5 which imposes singular 14 independent conditions, 14 general point. So this Z, any 14 point of Z fails to impose independent conditions.
The argument is that if it did impose general conditions, independent conditions, then you could move it to general position. Is that right?
Yes, yes. Independent conditions for O5. It's a degree 5 for the sections of. Yes, so this says that any hypersurface of degree 5 which is singular at 14 general points, then it is that doesn't exist. So if there exists a hypersurface which is singular more than 14 points, then that has to be, it's not general.
I mean, why not general? Why is that not imposing independent conditions? It could be different, not general in some other ways.
General with respect to this hypersurface means it imposes, the general means here that it imposes independent conditions with respect to that.
That's the only generality condition for.
Sorry?
That's the only condition of general for
For O5.
For the Alexander-Hirschouitz?
OD. The degree D when said degree D surface.
I mean, for example, you don't know that the points are distinct.
Yeah, but we can move this point, right? So here maybe we can have to use some semi-continuity, sorry, upper semi-continuous, because these points in general positions, this is an upper semi-continuous function, I think. Something have to, that argument have to give. And the dimension is the least when they are in general. So next, this remaining is very easy. Yeah, here I'll use one theorem that suppose this theorem I just have 10 more minutes. So this one theorem, this is due to by Eisenberg and et al. So this says that, so let P Eisenberg P be a set of points in PR and let D is greater than or equal to 2 be an integer. So if for all k greater than or equal to 1, no dk plus 2 points of P lie in a projective k plane, then P imposes independent conditions in the forms of degree D. So here any 14 point has to impose independent conditions. So this by this theorem, So D is equal to 5 into 2, so no 12 points. So either, so this, in this case, so this imply either there exist 7 points lie on a line, or 12 points lie on a plane. But since this point Z lie in a sextic surface, so a line cannot contain 7 points, so it can contain at most 6 points. So the only possibility that there exists a plane containing 12 points. So this implies there exists a plane containing 12 points So then what we will do, we just choose another 3 points. So we vary the 14 points from the Z. So removing, so this say P1 to P12. So choose another set of points. Set of 14 points containing P1 to P9. Then we repeat the same argument. We can show that H contains 15 points of Z. So this 12 point plus extra 3 points from here. So if you continue this process, then what we get, that we can show that Z actually H contains almost all points except at most 3 points of Z. So continuing. So in other words, now that means H contains almost all points of Z except 3 points, and Z also satisfies Kalibak property. So if we take the residue, so let Z prime be the residue with respect to H, then it can contain at most 3 points. So then Z prime but it satisfies Kalibak, since Z satisfies Kalibak for O5, so Z prime will satisfy Kalibak property for O4. And therefore cardinality has to be 4 plus 2, 6, which is a contradiction. So that means H contains all Z. So Z contained in hyperplane, then from that, so what we shown that Z contained hyperplane, so from here it is easy to see that this is a section. So if Z is contains in hyperplane, then this is non-zero, and therefore H naught of E is non-zero. So that is the contradiction. Okay, I stop here.